Thank you, Adam. Good afternoon to everyone present today. And today's webinar is going to be about EMS, and we will certainly deal mainly with induction applications. Okay. Just as my colleague Adam had just mentioned to you guys that we will be recording this webinar, and the link of that webinar will be sent to you. So feel free to look at it again or share it with some of your colleagues who were not able to make it today. Also, we will be glad to answer any questions you may have at the end of this presentation. So as and when you have a question cropping up in your mind, please feel free to type that in the chat box, and we will answer them towards the end of this session. Okay. With this, without any further ado, let me start the presentation, which is titled EMS for Induction Applications. The agenda for today is as follows. We're going to look at some of the, what is induction, some basic things about induction that I guess most of you guys are probably already familiar with. Okay. And we will next see how induction is really some sort of a multi-physics type of problem. It has got both EMS, electromagnetics, as well as say thermal applications, and there are also a lot of induction applications that involve motion too. Today we will just restrict ourselves to doing magnetic and thermal. Okay. And then we'll take a look at why the product EMS, why is it probably a great fit for doing these kinds of simulation. Then I will walk you through a couple of examples in what we call as our product demonstration session. And then we'll briefly look at EMWorks and its portfolio of products, and finally we will open the floor for Q&A. Now really let's now talk about the topic of the day, which is induction. When you briefly want to explain to someone what is induction, this image here on the right side will give you a good idea of what it is trying to do. So in a nutshell, when there is a time varying magnetic field, whenever there is a change in the magnetic field, and then a conductor material is exposed to this change, then you will have some induced currents in this conductor material. Okay, this conductor material could be a coil, it could be a plate, it could be made of copper, aluminum, stainless steel, etc. Now, this is a principle called as induction. Now, these induced currents, they produce the field of their own, because a current carrying conductor produces a magnetic field. And the nature with which this field is generated is in such a way that it opposes the main field. Okay. So this interesting principle leads to a lot of applications in the world of engineering that makes use of this principle of induction. So again, in a nutshell, to be able to have some induced currents, you need to have, first of all, a magnetic field that changes with time. Okay. And you also need to have any kind of conductor material in the vicinity of this changing magnetic field. Okay, so these two are prerequisites for you to have any kind of induction. Okay. So with this, let's go ahead and take a look at some of the applications of induction. A major application that we will be dealing with today is the thermal applications of induction. Now, metallurgists have been using this for a while, and also a lot of manufacturing process where induction is used to heat metals, sometimes even to the extent of it reaching its melting point. Okay, so induction can be used for heating, and this application is commonly called as induction heating. Now this application can be further extended into our kitchen where you can actually use the principle of induction for cooking. It's probably not very common in the Western world, but probably catching up, but induction cooking has become quite a norm in a lot of Asian countries, and that's because it's far more efficient than other types of cooking. With regards to the amount of current used as well as the time taken for achieving the cooking, and hence induction stoves and cookers have become quite popular. Okay. Induction can also be used for what is called as non-destructive testing applications. Now these applications involve probably inaccessible regions or devices and pipes that are very small and difficult to manually inspect and so on. So we can use the principle of induction to design probes and equipments that are used to test material defects. And actually in the coming weeks we're going to do a whole series of an entire webinar dedicated to induction applications with respect to non-destructive testing. And then also can be used in some automotive and other moving equipment type of application is the eddy current braking. So whenever there is any movement that requires to be stopped without applying friction, induction is actually an excellent way of enabling that kind of braking. And in eddy current braking systems are now quite used in a lot of applications like elevator applications, maglev, train applications, and also machine design and automotive too. Okay. And finally, not but last the least, some of the applications, the early applications of induction are still prevalent and valid today as they were, several decades ago. Electric generators and transformers, they use the principle of induction for their working. Now, as I mentioned earlier, today we will probably we will have the time just to look at induction heating. And I'm going to illustrate that with two examples. One is the heating of metals using induction, and other is the design of an induction stove or induction heating device, and how that performs with regards to the current consumption and so on. So we're going to be looking at these two examples right now. Now, before we do that, induction is actually, as I mentioned here, is a multiphysics approach, right? Why? Because induction, as the name implies, it actually induces or produces what is known as eddy current or induced currents in the metallic structure, especially in metals, conductor materials, right? Now, this eddy current produces some kind of heat. It's sometimes it's desirable in the case of induction heating. Sometimes it is undesirable in other applications where time-varying magnetic field will produce heat, which is not desirable. So now this, whenever there is a production of heat, there is going to be temperatures, rise in temperatures, and it's important for us to monitor, as engineers, to monitor what this temperature is and this rise in temperature is. So it's basically an electromagnetic and a thermal type of problems. Okay. Now EMS can handle this very well, and also to mention that EMS is capable of doing both steady state as well as a transient thermal type of application. Now, so what are some of the advantages of EMS as your preferred solution for these kinds of simulation? Is basically EMS is integrated inside SolidWorks as well as Autodesk Inventor, and it can seamlessly handle geometries from any CAD, especially the ones created in these two products as well as the ones that you can bring from other CAD geometry, because these SolidWorks, Inventor, etc., they open multiple CAD formats. And you can simulate real-world models without any simplification. You don't need to export your models out if you created them in your SolidWorks or Inventor platform. And it's capable of dealing with multiphysics, as I mentioned, mainly as today's topic. It's in electromagnetics and thermal, and also it can handle motion as well, and that's a topic for a different date. And there are also past webinars where we have done coupled electromagnetic and motion simulation that you can refer to in our website. Okay. And finally, you can obtain all the engineering results in one location right inside your CAD system. We're talking about the flux densities, we're talking about induced currents, we're talking about temperatures, etc. So different simulations, electromagnetics, thermal, etc. You can all of them manage inside one UI and one interface. With this, let me move quickly to some product demonstration. I'm going to be shifting my screen now to SolidWorks. Okay, the first application that we are going to look at is the induction heating application. As you can see in my screen, what I have is a coil design that has been done specifically to heat bars. These are conductor bars. They're made of aluminum and or stainless steel, etc. You can heat these conductors using the coil. Now we have to study a couple of things. The objective of this simulation is to really understand how much of current do I need to pass through to be able to heat this bar to a desired temperature. And number two is, what is the frequency with which I need to pass this current. Note that to be able to produce a time varying field, you need to supply a time varying current. In this case, the most easiest time varying current that is available is AC currents that you can draw off your mains. So now that AC currents is supplied in 50 or 60 hertz depending on where you are located. But you can have electronics that can amplify, change the frequency of this time varying current and supply it to this coil. So the idea is to understand, okay, if I use 60 hertz, what type of heating characteristics would I get? And if I use a very high frequency value, like say 250 kilohertz, how is the heating performance going to be with the same value of current? Yeah, we're going to use about 300 amps to heat this thing. So let's see how this is done inside EMS. Now, as you see here, this model has been designed using SolidWorks. Okay. It has two components. One is the coil, as you see here, highlighted in blue, and other is a heating rod. This is the rod that needs to be heated. Now we will pass current through the coil, and then we're going to see how hot this bar gets. Now, to do your electromagnetic simulations, one need to go to what is known as the EMS Manager tab. So when you go to the EMS Manager tab, you can organize your simulations inside this tab. Okay, this is where you would do your electromagnetic and thermal type of simulation. Now, the first step in doing any kind of simulation is to create what is known as a study. Now, you can create a study. EMS has several different study types, but for induction type of problems where you have an AC current, you're going to refer to what is known as the AC magnetic study. Okay. And you can specify the frequency here. We can start with 50 hertz, and then we can keep increasing it to a higher level. I do want to let you know that the program is capable of simulating several hundred kilohertz and even up to a few megahertz frequency. It's possible to simulate using this program. Now, if you want to couple to thermal, you can couple to thermal. You can couple to both steady state as well as transient thermal. The difference being is the steady state thermal is going to give you the steady state temperature that is actually reached after a very long time. You have no idea about how long it takes to reach the steady state temperature. That's the steady state solution. You can also do a transient solution, which probably is more important for a lot of engineers, especially in the area of induction heating. Is really you want to understand how long does it take for you to heat this to a particular temperature, or okay, after a certain amount of time, how much temperature has been reached. So you can do both steady state as well as transient. Okay. Now, once you have created a study, it creates what is known as a study tree, as you see here. Now, this study tree, the first step that is involved is to create materials for each of your components that you see here. Now, the coil is made up of copper, and applying materials in EMS is extremely simple. You can go ahead, apply materials. EMS has its own material library that comes pre-populated with all the different commonly used materials in the electrical industry. As you can see here, we have cables, ceramics, conductor materials. This is where you would select copper from. and all the material properties are available for you. Then you also have some ferromagnetic materials, you have nonlinear steels with its BH curves and so on. So EMS really has an exhaustive material library. And needless to say, this is a fully customizable material library, which means that if you don't find any of the materials that that maybe you are designing using, then you can create those materials and then use them for simulation. Now the bar is made up of mild steel, okay, and you have this little lightning symbol here, which really tells the program to compute the eddy currents on the components here. So the program will calculate the eddy currents on the bar as well as on the coil. Now as far as the current input goes, it's done through what is known as coil definition. Now when you're doing a coil definition, you simply select the component that comprise the coil. You select the phase through which your current is going to come in. In this case, as you see here, let me just reduce this a bit so it's palatable. So the current goes in through this and comes out through this port. Okay. And the RMS value of the current is going to be about 300 amps, and this is the current that is supplied here. Now finally, this is a coupled thermal solution. We really like to understand, okay, what is the temperature, the steady state temperature reached in the mild steel bar in this particular example, and that's done using, and then there is a convection boundary condition that is set. So everything that is in contact with the air is actually convecting with the natural convection, and the outside temperature is about 300 Kelvin. So with this, we have created what is known as the study. Now these constitute the inputs to our simulation. Now the inputs are done. Now we can run the simulation and take a look at the results. Prior to this webinar, I took the privilege of running these simulations so that we could go directly into the results. So let's go ahead and look at the results. Before we get to the results, I do want to emphasize here that EMS is a finite element based simulation package. Now what does that mean? It means that it creates what is known as a finite element mesh. Now EMS has automatic mesh creation tools, and where it is capable of creating the mesh, generating the mesh automatically. The most optimized mesh for creating good results is produced, and then this is used to give you the results. Now let's go ahead and quickly take a look at some of the results. So what are the results that one can look at? Certainly one can look at the flux density. The magnetic flux density can be visualized. You can see here how the magnetic flux density varies in the bar, okay, and even more important, one can look at the current density. Now this is the current density. These are the induced currents that you can see in the bar. And finally, we are interested in the temperature. So at 60 Hertz, you can see here the coil gets heated close to about 300 Kelvin, but you can see that the bar hardly gets heated. So if you want to just go ahead and isolate the bar to understand what are the temperatures on the bar, and you can see this is the temperature distribution and the value. So really hardly, it's only a 7 degree Kelvin rise over the ambient temperature of 300 Kelvin. So really it establishes a fact that at this high 300 amps current, the frequency of 60 Hertz is certainly not the frequency that one would use for induction heating. So for induction heating applications, you're going to use high frequency AC current. Okay, now what do you mean by high frequency? I did a similar study now using 250 kilohertz. Okay, so when I created the study, I can input the frequency in hertz. Now this is 250 hertz, which is 250,000 hertz, which is 250 kilohertz. Okay. Now it's again coupled with thermal simulation. As before, the materials are the same, and the coil, as you see here, the definition doesn't change. You know, the current still comes in through the top leaves to the bottom. There is still 300 amperes of current, RMS value, but the difference was that this is now very high frequency current. So there is the magnetic field varies rapidly, and this induces a lot more eddy currents than before, and hopefully will raise the temperature much higher than what we saw before. Okay, now let's go ahead and take a look at the results. Let's start with the current density plot. You can see now this eddy currents a lot more distributed than before, and also the value is close to e to the 7 amps per meter square. Okay, we can go ahead straight away, take a look at the temperature. Now you can see the coil is heated around 320 Kelvin as before, because that only depends on 300 amps of current going through it. But you can see that the rod is now heated well past 450 Kelvin. Okay, so this heats the rod to a much higher temperature than when you used 60 Hertz. Okay. So you can do a lot of what-if scenarios using EMS. Now you can really vary the frequency, you can vary the current, you can change the shape of the coil to see how that affects vary the pitch of the helix and the diameter and so on. So a lot of what-if scenarios that a typical engineer would do can be actually done using the solid modeling capabilities in SolidWorks, and immediately translated into electromagnetic results based mainly in the form of what is the temperature and so on, and this is going to be highly beneficial to us. With this, let me go ahead and open up the next model that is of interest to us, which is basically an induction stove design or an induction cooktop design. Now here we have what is known as an induction cooktop. Okay, this is not the full range, but most of the important materials that are there in an induction cooktop is actually represented in this CAD geometry. Okay, so there is obviously the vessel that is kept on a ceramic base, and that's really not a conductor at all. You could actually even touch it while the apparatus is operating, and it's hardly any heat there. Okay, so this is the ceramic base, that's an insulator, and then let me just go to now this is the configuration where there is the coil. So we have a half a coil here as we show here. One could actually take a look at both the coils. So there is this coil. This is a wound coil, as you see here. That's that is placed on some iron type bottom base, and now this is a coil which is excited. Now this coil, let's just revert back to the default configuration. Now this is a coil which is actually bringing about the heating that happens in the pan. So the idea is for us to understand, okay, let me rotate it, the coil that you see here, it's in the bottom, and the coil, as you see, is not in contact with the pan. So it's not through conduction that this is actually heated, and most people wrongly think that, okay, we're placing the pan on top of the coil, and hence that's what is causing the transfer of heat. No, it's actually not the case. The coil, in fact, doesn't even touch the metallic portion of the pan. So, and there is a good layer of insulator that separates the pan as well as the coil. Okay. Now, in this particular example, our idea is to understand a couple of things. Now, we will introduce you to the transient nature of thermal too. So as before, let me just go ahead and go to the EMS tab. Okay, we are interested in a couple of things. One is, okay, how does my temperature change every 60 seconds? Okay, I want this pan heated up to a temperature of say 70 degrees or 75 degrees centigrade, which is pretty much the the temperature at which the for us to reach this temperature, and you know, what is the distribution of temperature inside the pan, and how does it look, and so on. Okay, if you look at the materials that we used here, there's a lot of materials here, but the main things are the copper. The coil is made out of copper. Okay, then there is the frying pan body that is made of stainless steel. Then there's the handle that could be made out of alumina. And then this is the ceramic top, which is complete insulator. It's an insulating material. You can even see what is the temperature of this ceramic top. It's hardly much, so that gives you the comfort that you can actually touch this, and there's going to be nothing happening. And there's going to be these iron cores that are placed on which the coil is placed. Okay. Now these are some of the components here. As before, we have the coil definition. So we select the components that comprise the coil, and then we select the face. In this case, it's a wound coil that's wound, and so this is the face through which the current comes in, and it circulates here. Okay. And as far as the properties of the coils are concerned, it has got 28 turns of copper, and it carries a current of about 8.5 RMS value of current. Okay, let's revert back. As far as the thermal properties are concerned, it's just convecting. All the surfaces that are in contact is just convecting to the ambient air, which is kept at 300 degree Kelvin. Okay. As before, EMS has an automatic mesh generation capability that generates the most optimal mesh for your solution. So that's quite automatic. We also have some mesh controls. You know, you can actually control the size of mesh in different components. That feature is also available in EMS. Now let's go ahead and take a look at the results. Now basically we are interested in the thermal results. So what really happens after 60 seconds? So now this is the distribution of heat after 60 seconds. You can see here that there is a region of your vessel that is heated to the maximum. That's shown in red. That's almost 45 degrees Celsius. Okay. It's not very hot, but after 60 seconds at this particular value of the current, this is the temperature that is reached. Okay. Now after 2 minutes, 120 seconds, you can see that the temperature goes up to about 56 degrees Celsius. Okay. And after 3 minutes, it goes up to 65, and after 4 minutes, we reach about 72 degrees Celsius, and this is really the temperature that we want, and this is a temperature that's very comfortable for cooking. So it takes about 4 minutes for us to reach this particular temperature for our design of the coil, and also the current that is input, which is about 8.5 amps. Okay. And if you see here, the frequency is about 24 kilohertz. Okay, that's really that's around the frequency in which these induction cooktops operate, about 20 to 25 kilohertz. Okay. So this is fine. This gives us an idea, and you can really see this ceramic cooktop, and it hardly reaches a few degrees more than the ambient temperature, and that gives you the comfort that it's not really the conduction. There's no heating of that top plate here. It's really not going to cause any concern, burns, etc. Due to that heating. Now I also did this as a steady state problem, just to see what is the maximum temperature this particular pan is going to reach to. Okay. And this is after a very long time, maybe after about 4 or 5 or 6 minutes. It can reach up to 130 degrees Celsius. Okay, and really that's why you need to have some kind of a thermostat which regulates the current and cuts it off, because now this is very high temperature as far as oil is concerned, and it certainly makes the oil boil. Even water boils at this temperature. So you do not want to leave this on for a very long time, and hence these things have time sensors or also even temperature sensors that senses how hot your surface of the pan, etc. gets, and this enables us to cut off the circuit. And even at this steady state temperature, you can see that the cooktop, which is basically a insulating material, really doesn't get all that hot. I mean, maybe it reaches about 45 to 50 degree Celsius, but nowhere close to something that is dangerous for humans to handle. Okay. So this is really what we wanted to show you today. Is the induction applications associated with electromagnetics and thermal. So let's go ahead and revert back to our PowerPoint here, and we're going to take a look at the products and bundles offered by EMS. Now EMS comes in two flavors. One is EMS Professional, other is EMS Premium. The EMS Professional has 6 different solvers. Okay, we have the electric solvers, which is the electrostatic, electric conduction, AC electric, and then we have the magnetic solvers, which is magnetostatic, AC magnetic, and transient magnetic. And just to remind you, today we used AC currents. Basically, that's induction. Most induction applications make use of AC currents, and then the module that and the solver that you will be using mostly is the AC magnetic. Okay. You can couple them to thermal. If you're interested to find out what is the temperature distribution, you can couple that to motion. On a later webinar, we'll probably do eddy current breaking, etc., where one can see how a coupled motion and EM simulation helps you to understand what is the braking force and so on. You can couple that to structural simulation. And EMS Premium is a package that comes with all of these coupled simulation along with parameterization that helps you to parameterize your geometry and other things like current, number of turns, and so on, which helps you to do a lot of automation and a lot of what-if scenarios in your program automatically. We also have a product called HFWorks, which is certainly not the topic for the day, but in case you are interested in any high-frequency electromagnetic applications like design of antennas, waveguides, etc., we have separate webinar series for HFWorks that you should attend, and you can get more information on it on our website www.emworks.com. With this, I want to come to an end of this presentation, and what did we use today? It's kind of important to know what you saw here. What are the products that you need to be able to do a similar simulation? You need SolidWorks 3D CAD, the basic package. Okay. The current version of EMS is EMS 2017. The current version of SolidWorks is SolidWorks 2017. But EMS 2017 works with SolidWorks 2017, 16, as well as 15. So you need to have SolidWorks that is 2015 or greater. We used EMS Professional because we used the AC magnetic solver, and also we had the thermal add-on, which enabled us to look at the temperature distribution. So with this, I would like to thank you all for your time today. It was wonderful having you here, and I hope this webinar was informative. There are a lot of videos in our YouTube channel. We encourage you to visit them and watch them at your leisure. And if you have any questions, please direct them at sales@emworks.com or call us toll free at 1-800-397-1557. With this, we will actually open the floor for some question and answers that were there. So if you have any questions, you may want to send them to us in the chat window, and I'll be happy to answer them. So one of the questions that was asked is, do you need to have a separate package to do thermal? It's a separate add-on package. Yeah, there is an additional charge to thermal, but the thermal simulation and the solvers, all of them are residing inside EMS, which is an add-in package to SolidWorks or Autodesk Inventor. So you can do a coupled EM and thermal simulation without any additional package that you can. Then if there is any other questions, I'll be happy to answer them. Okay, with this we come to an end of this webinar, and thank you all, and a recording of this webinar will be posted to you. Should you have any particular questions after this webinar, just feel free to give us a call, or we'll make sure that one of us get in touch with you to understand your application and see if EMS is a good fit for your needs. Okay. With that, we come to an end, and thank you very much.